This meta-model diagram illustrates the theoretical relationships between bounded contexts in domain-driven design. Drawing a conceptual map like this on a whiteboard is deceivingly easy. You sketch circles, draw lines connecting them, and everything looks perfectly cohesive. But turning this abstraction into functioning code requires a completely different approach. Developers often fall into what we can call the noun trap. They scan a list of business requirements, tick out every single noun, user, invoice, product, address, and map them one-to-one into database tables, giving every single concept its own unique UUID. Then comes the secondary trap, taking every line drawn on that whiteboard and treating it as a bidirectional relationship that the codebase must explicitly support. By treating every concept as an equal object and linking them all together, the domain model degrades into a highly coupled, unmaintainable CRUD architecture. It becomes a giant, glorified table editor. That create, read, update, delete approach collapses the moment you introduce complex, evolving business rules. When everything is connected to everything else, updating a single status on an invoice risks triggering a cascading failure across the entire system. In Chapter 5 of Domain-Driven Design, Eric Evans lays out a clear thesis to solve this. An abstraction only becomes working software when you make definitive, restrictive choices about how things interact. You had to abandon the idea of mirroring the messy, interconnected real world in your code. The real world doesn't have sharp boundaries. Your software must. To enforce those boundaries, we have to ask 3 ruthless tactical questions of our design. First, which of these relationships actually matter to the business? Second, which objects possess a continuous identity over time? And third, which objects are simply descriptive values? Making these highly restrictive choices, defining exact traversal directions, strict identities, and absolute immutability, eliminates accidental complexity. It is the only way to make a complex domain tractable in code. Let's start with relationships. In software, every traversable association you create is a tangible mechanism. It is an object pointer in memory, a join in a SQL database, or an encapsulated repository query. Leaving relationships unconstrained creates a massive technical tax. If cargo and customer traverse to each other at will, you generate a chaotic cascade of database calls just to load one object. The first rule of constraint is to explicitly impose a single traversal direction. This mirrors how real business processes work. In logistics, the customer dictates the cargo's requirements, but the cargo doesn't dictate the customer. Only one context influences the other. The second rule of constraint is to add a qualifier to reduce multiplicity. Take a look at this logistics model. We have an itinerary that contains a vast, ordered list of transport legs. If we leave this as a simple one-to-many association, our application has to load the entire history of a shipment's transport legs just to find a single departure point. That is a massive drain. We fix this by qualifying the association. Instead of loading everything, we ask the itinerary for legs matching a specific load or unload location. By applying that qualifier, the underlying database query is restricted to a precise parameter, drastically shrinking the memory footprint and simplifying the code. The third and final rule of constraint is the most effective: eliminate the association entirely. Developers are often afraid to delete relationships. They falsely believe that if a connection exists in the real world, the code is incomplete without it. If a relationship isn't essential to the immediate job at hand or to the fundamental meaning of the object, it is a liability, not an asset. Limiting these traversal paths is a critical defense mechanism. It protects database performance and enforces strict boundaries between your modules. Once relationships are constrained, we have to look at the objects themselves. A common mistake is assuming an object is defined by its current data attributes. An entity is a concept defined exclusively by a thread of identity and continuity over time, regardless of its data. It has a life cycle. It can go through radical state transformations, moving from in transit to customs to delivered, while conceptually remaining the exact same thing. Think of a bank transaction. It might start as pending, move to processing, and finally cleared. The attributes change completely, but the transaction ID must remain unbroken. If you lose track of that continuity, the engineering consequences are severe. Mistaken identity leads directly to catastrophic data corruption and race conditions. You cannot rely on automatic language features to handle this. In a distributed business domain, checking if two objects share the same memory location tells you nothing about whether they represent the same conceptual invoice. Finding a reliable, unique identifier requires deep analytical effort and an understanding of the business domain. You can't just attach a database auto-increment integer to an object and assume it has an identity. Identity is an architectural choice. It is entirely dependent on the specific bounded context you are working in. Consider a ticketing system. When a fan is booking a ticket, seat 42A must be modeled as an entity. Its identity is critical to prevent double booking. But pass that exact same seat to a stadium maintenance application, and its unique identity might not matter at all. To the cleaning crew, a seat is just a descriptive value, a plastic chair in a row. Forcing an artificial identity onto an object that doesn't need one creates massive, unnecessary tracking overhead for your system. By artificially isolating true entities from general objects, you prevent catastrophic state tracking bugs in highly transactional systems. That brings us to the objects that don't have an identity, value objects. You use a value object when you only care about what it is, not which specific instance it is. Value objects possess zero conceptual identity. They exist to implement Ward Cunningham's whole value pattern, where independent attributes are grouped into a single cohesive meaning. Take a financial application. The number 50 million and the word dollars mean nothing separately, but snapped together, they form a conceptual whole. The primary technical constraint that makes value objects work is absolute immutability. The rule for state changes is strict. You never mutate a value object. If the data changes, you completely replace the object with a new one. This constraint enables side effect-free functions. You can run operations that compute and output results without ever modifying the underlying state of the object. The engineering payoff is enormous. Because they are immutable, value objects can be freely copied, shared, and passed across threads with absolute security. You don't have to write complex database locking mechanisms or track state changes across a lifecycle, the way you do with entities. Aggressively converting standard objects into immutable value objects drastically shrinks the surface area for bugs and side effects in your codebase. This UML class diagram shows the result of applying these constraints. You stop drawing messy, interconnected webs and start building refined, layered architectures that strictly separate concerns. Audit your models with a concrete checklist. First, the entity test. Is it the same concept if its data changes completely? Second, the value object test. Does it merely describe a thing? Third, the association test. Must the software navigate this relationship for business logic? Attempting to perfectly map the interconnected physical world into code always leads to failure. A great domain model doesn't mirror reality. It relies on imposing strict artificial boundaries through constrained associations, an explicit identity, and immutable values to make the chaos of business perfectly tractable in code.